So I'm Scott Ransom. I'm at the National Radio Astronomy Observatory in Charlottesville, Virginia, and also at the University of Virginia. And I have to admit, I have a problem. My problem is that I'm obsessed with pulsars. And as many of my colleagues here know, that is definitively true. And I'll tell you during this talk, hopefully, why that is, why I'm obsessed with them. And unlike Jay, I have no problem with using the A word about these objects. These are freaking awesome. Hopefully, you'll get that from my talk. So the way I'm going to start this out is with a hero of mine, and that's Jocelyn Bell. And hopefully, many of you in the audience know that name. If you don't, I implore you later tonight or sometime soon to go on the internet and look up her story. She is the discoverer of pulsars. This is a picture of her when she was a graduate student back in 1967 in Cambridge. And her advisor and her and several other people built this radio telescope. And yes, that's not a fence behind her. That's a radio telescope. Because if you observe radio waves at long enough radio wavelengths, you can build them out of regular wires and fence posts effectively. So this whole thing in the background here is all a radio telescope. And it was constructed so that they could measure quasars, which have recently been discovered. They were going to monitor how bright these quasars were as a function of time. They were looking at the variability of these quasars. And so the way this telescope worked is the radio signals would be output through an old-school pen-style chart recorder. So the intensity of the radio waves coming into the telescope as the Earth rotated would be written as little wiggles on this pen chart recorder. And what Jocelyn's job was, as a graduate student, was every day she would take the tens of meters of pen chart recordings that had been recorded, and she would try to figure out where are the quasars as they rotated over, how bright were they, how big the wiggles were, and to try to figure out what are the astrophysical sources, the quasars, and remove from them the huge number of terrestrial interfering sources that she saw. Because even our modern society, even back in 1967, we produce a whole lot of radio interference. Spark plugs from cars, sparking electric fences, you name it, can cause a whole bunch of extra wiggles in the data. And what she did very, very carefully was found a very strange and anomalous signal, which she thought was astrophysical. And the great thing about predicting that something's astrophysical is she was able to say, on this certain night, it should be visible at this time. And lo and behold, when she and her advisor went back at exactly that time, they saw little blips on the chart recorder about once per second with clock-like regularity. And that was the astonishing thing, because quasars were thought they would see variability on hours, maybe, certainly on days, weeks, and months timescales, but no one expected to see radio signals varying once per second. That was astonishing. And it turned out that they had made one of the biggest discoveries in astrophysics, or even physics, of the last century. So what did they find? They found these guys. This is a cartoon version of a radio pulsar. It's a type of spinning star. I'll talk about it in more detail. As it rotates, it's like a lighthouse. There's a beam of radiation, and as it sweeps past, we see a pulse of radio waves. In this case, we've also taken that radio intensity and put it into a speaker so you can hear a blip of the sound as well. So where do these things come from? What types of objects are these actually? Well, we've heard about the way that stars are effectively devices for transforming hydrogen into heavier elements. That's what they do via the process of fusion. And most of the stars in our galaxy are these little puny guys. Here's our sun. But as you go to bigger mass stars, such as these big guys here, they're going to eventually, at the end of their lifetime, when they fuse all their hydrogen, they'll explode as supernovae. And Lars talked about that beautifully earlier in the day. The core of those stars, though, are transformed during this process. That's what happens in a supernova. It's the transformation of the core of a star into what's going to be effectively a pulsar. And what you get, right away at least, are these. And you've even seen a picture of the Crab Nebula earlier as well. Here's the ejecta from the supernova, But what Lars didn't mention earlier is that almost all the glow that you see in this image, and this image shows wavelengths clear from radio waves, clear up to X-rays, all of that energy, all of that glow is coming from this central object at the very center here. That is a pulsar. That pulsar is energizing that nebula, causing it to glow. So these are really amazing objects, and what that is, what that core transformed into, is a neutron star. So what are these neutron stars? Well, they're incredibly exotic objects. Some of the most exotic objects in the universe, period. And one of the things you've heard earlier is that black holes are very exotic, but they're simple. They really only have mass. They're the curvature of space and time. These actually have a surface, they have magnetic fields, they have a bunch of interesting properties that we can measure. So for one, these have the masses of everything in our solar system, but all at the size of a city. That means they're extraordinarily dense. They're the same density, or even denser, by a factor of a few, than atomic nuclei. So if you think about it, you have a giant nucleus made almost exclusively of neutrons that's the size of a city. That's extraordinary. And that causes a lot of other special things. You have a tremendous density. There's an incredible high surface temperature. These are about 1,000,000 degrees Kelvin, so they emit in the X-rays. That density causes an incredibly strong gravitational field. Lewis talked about this earlier when he talked about dropping the clicker and how that would release the energy of a nuclear bomb. It's 1 billion times stronger gravity than the surface of the Earth. That's extraordinary. That's a big number, 100 billion times. Even more mind-boggling to me, and I study these all the time, is that these can rotate up to 700 or more times per second. That's faster than a kitchen blender rotates. That's faster than a race car engine rotates. And yet these are the size of a city. And these objects that spin very, very rapid, these are the ones that I personally concentrate my research on, the so-called millisecond pulsars. The blue that's in the background, all this blue, these blue curves, these are the magnetic field lines. And as you rotate that magnetic field, which is incredibly strong, it can be billions, trillions, or even quadrillions of times stronger than the Earth's magnetic field, that causes these radiation beams that are coming out of the poles here. These radiation beams that sweep like a lighthouse. And those are what we actually measure. Typically, it's in the radio waves, but you can also see X-rays and gamma rays as well. And the amazing thing is that all this energy that's coming off these objects is purely coming from the spin of the object, from the rotation. And that can be as much energy as 10,000 times the amount of output of the sun, purely from rotation. These are giant flywheels in space. And for the millisecond pulsars especially, they're basically perfect clocks. And what I like to do is use these clocks to do extra physics, use them as tools to do cool physics. And we do that by a process known as pulsar timing. And the pulsar timing, the way it works, is that blue sentence at the top of the slide. We unambiguously account for every single rotation of the pulsar over timescales of years. And if the pulsar is rotating hundreds of times per second, like a millisecond pulsar does, and the Earth is moving around the sun, and the pulsar is moving across the sky very slowly, and the pulsar is moving in orbit around another star, you have to do a whole bunch of things to count pulses very, very regularly. And our data kind of looks like this. We see individual pulses, and you can hear when those pulses are arriving. So what we're going to do now, to try to explain a little bit how this works, is we're going to do a little bit of an audience participation exercise. So it sounds really amazing how you might model how these pulses are going to arrive, especially if we can't observe a pulsar all the time. For instance, I go to a telescope and I observe today, but I don't observe for the next week or two. How do I know how many pulses are coming during that week or two when I'm not observing? Well, the way we do it, just like Bart was talking about last time, it's the way science works. We have a model that we build to explain our observations. That model lets us then predict what's happening in the future, which we can then check when we go back and observe again. So what we're going to do with this sound bite here, we're going to play that pulsar sound. I want you to get the rhythm of the pulsar in your mind. Don't clap or anything because you'll screw it up for everyone else, but keep it in your mind. Think of that pulsar going, and then the pulsar is going to go away. That's like you going away from the observatory. You're going to sleep for the night or going on vacation, whatever. And then it'll come back again, and what I want you to tell me, first off, is two things. How many pulses did you miss? How many pulses were there when you weren't hearing it? And second, how close were you keeping time with your mind when the pulse comes back? Were you right on the beat, or were you a little bit off? So you can go ahead and play the sound. How close were you? Were you right on? How many pulses were missed? I heard a whole bunch of answers. The correct answer was 10. There were 10 missing pulses, but that's why I'm a pulsar astronomer and you're not. Anyways, so, but the amazing thing is, though, when you do this modeling correctly with high-precision pulsars and computers, you can get incredibly precise results. And let me show you an example of that. For millisecond pulsars, these can be some of the most precise clocks that we know about anywhere, as good or even better than some atomic clocks. So what do I mean by that? Well, this particular pulsar is one of the best measured pulsars that we know of. It's a famous millisecond pulsar. Don't worry about its number. But at 3:05, I'm 5 minutes off. In 5 minutes, this pulsar will have a spin period of exactly 4.5701365229, etc. milliseconds. But I'm an observer and a scientist. We need error bars on our measurements. When I put an error bar on the measurement, this is the error bar. 2 in that last digit. These are some of the most precise measurements in all of physics. And if we can track that period incredibly precisely, we can do really cool things with it. Like I said, the pulsars are slowing down because they're giving off energy. That means that number's changing. Like the odometer on a car, it's slowing down. That number's getting bigger. So how much is it changing? Well, that very last digit, this one right here, changes by about 1 every 2 minutes. Just like an odometer. And if you think about what that means that this digit right there, it takes 4,000 years for that digit to change. So those first 6 digits are effectively constant for thousands and thousands of years. That's why we can use these things as perfect clocks to do physics. So in my last couple minutes, I'm going to just give you a flavor of the type of physics that we can do with these objects. You've heard about how Einstein's theory of general relativity is a warping of space and time. Well, if we have a pulsar that's in an orbit with another star, that warped space-time means that the orbits are not ellipses, as Newton and Kepler would have predicted. They're close to ellipses, but not precisely. And that means the orbits change with time. We're using pulsars with this highly precise clock. We can measure exactly how these orbits change with time. And that lets us test general relativity. And in fact, this is exactly what Russell Hulse and Joe Taylor did. That was Vicky Caspi's thesis advisor, Joe Taylor. They won the Nobel Prize for making exactly that measurement and showing that the orbit was shrinking exactly as predicted by general relativity because they were giving off gravitational waves. And I should mention that's the second Nobel Prize that pulsars have won. The first Nobel Prize was for the initial discovery of pulsars by, who do you think? Not Jocelyn Bell. Jocelyn Bell's advisor, which is a whole other story. But these are some of the types of things we can do with general relativity. We can measure the masses, we can determine the properties of these pulsars to incredible precision, and even do nuclear physics to tell us what's going on at the centers of these objects. And then my very last slide is my very long-term project that's going on that I'm part of, and Vicky is as well. It's called Nano Grav. And with this project, we're trying to directly detect gravitational waves that are coming from supermassive black holes that are starting to merge when 2 galaxies have merged, because these supermassive black holes are at the centers of galaxies. And they make very long period gravitational waves that are like years long. And the Earth then kind of is riding on this sea of gravitational waves. And the measurement is actually quite simple. If there's pulsars spread all over the sky, and let's say you guys are all pulsars and I'm the Earth, if gravitational waves makes me jiggle the Earth closer to you as pulsars, your pulses are all going to be a little bit early. The pulses from the pulsars behind me are going to be a little bit late. The pulses from the pulsars on the side don't get changed at all. When I jiggle back this way, it reverses. So over the time scale of years, we can measure directly, just like LIGO has, the gravitational waves from these supermassive black holes. And we've been working on this for over 10 years. These are for very, very slow gravitational waves. And we think we're very, very near a detection. This would open up a second window into the gravitational wave universe and allow us to see something, the near collisions of supermassive black hole binaries that are almost impossible to measure in any other way. So I'll end there, and hopefully you'll see why I'm kind of obsessed with pulsars and why I think they're freaking awesome. Thanks.